So we're going to introduce a new concept called a vector space. Thanks, Croy. So this is on vector spaces and subspaces. And so we begin with kind of this abstract concept of what a vector space is. And there are these 10 different conditions that are all true for subspaces. So I'm going to read, what I would like to do is read the definition and maybe the first statement, and then I'd love to have maybe people unmute themselves and just read one statement, and we could have kind of read round robin on the next bit to help people stay alert through this section. So definition: a vector space is a non-empty set V of objects called vectors on which are defined two operations called addition and multiplication by scalars. That would be real numbers. And it's subject to the 10 axioms or rules that are listed below. The axioms must hold for all vectors u, v, and w in V, and for all scalars c and d. So for example, the first axiom is that the sum of u and v, denoted by u plus v, is also in the vector space V. So even if we were in a face-to-face class, I would tell you, please don't memorize this. It's important, but it's not the kind of thing that you have to have on the tip of your tongue. So let's keep going and add a couple of other principles and try to get some examples here. So it also follows that 0 times u is equal to 0. And just so that you're noting it, this would be the 0 vector. And c times the zero vector is the 0 vector. Last would be that negative u is what when we say that, we're meaning -1 times u. So just kind of a shorthand notation. Famous vector spaces, ones that you're used to. So the space Rn, for n is greater than or equal to 1, is probably the best examples of vector spaces that you're familiar with. And so we're going to, when we talk about vector spaces, much of the time we're going to be picturing either R3 or R2. So those are ones that we can picture, but there are definitely other vector spaces, as you will soon see. So I want to discuss whether the set of polynomials Pn is a vector space. So first of all, let's make sure you understand what this Pn would mean. So for example, P2 is the set of quadratics. It's a set of quadratics of the form, think maybe at squared plus bt plus c. These aren't equations, they're just polynomials. Or P1 would be the set of all lines. And this includes through the origin and not through the origin. So this would be like at plus b, or P3 would be cubics at cubed plus bt squared plus ct plus d. So Pn would be the set of nth degree polynomials. And so I would write these as, I could write a couple of them. Pn is maybe like a0 plus a1t plus dot 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 plus antn. So it's like a nth degree polynomial. If I wanted a second one, I could call it Sn, and it would be b0 plus b1t plus bn t to the n. So if we want to figure out whether we've satisfied these axioms, we could look at, say, axiom number 1. We could say, let's take two of these things, Pn and Sn, arbitrary things, and see whether it's still in the space. So if I take Pn and Sn and I add them together, I'm going to get a0 plus b0, a1 plus b1, this is an nth degree polynomial. So we would say this is still an element of our set. And if I want to describe the set, now I'll use the double bar P, and I get my little n at the bottom. So it is an element of the set of nth degree polynomials. So axiom 1 It's true, it holds. Maybe let's look at axiom 4. So axiom 4 is the one that says there's a 0 vector. Is there a 0 in Pn? What would it look like? How do I get a 0 polynomial? Yeah, from Evan and from Felix and from others. So you've got, I actually like the way Evan wrote it. So you'd have 0 plus 0t plus dot, 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 plus 0t to the n. This is the 0 polynomial, and it certainly is in Pn. So axiom 4 holds. It's also true. Maybe let's look at axiom 6. So axiom 6 is the one that talks about scalar multiplication. And so we could look at C times Pn. So this would be like C times A1 plus, A naught plus A1t plus dot, 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 plus AN t to the n. And that's going to be equal to C A naught plus C A1t. We call this cat1, in case you're wondering, plus dot, 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 plus cat n to the n. And you could probably pretty easily see that all these yellow things, these are all just coefficients on a polynomial that once again lives in Pn. So axiom 6 is also true. And so we could go through all 10 of those axioms and verify in the end that yes, Pn is a vector space. All right, so this example 1 that I want to kick off with should be familiar to you, but really what it's doing is it's focusing in on something that is this familiar. We're doing something you've done before, it's just talking about it in a new way. So let V be the set of all vectors. Those would be directed line segments in 3-dimensional space with 2 arrows regarding as equal if they have the same length and point in the same direction. So if we have two guys like this, we would say both of those would be equal. Okay, sound familiar? These are like your old friends, the vector. We're going to define addition by the parallelogram rule. And so our parallelogram rule says if we have vector u here and we have vector v there, then we can kind of do that tip to tail thing. And this red vector would be our u plus v. Okay. Parallelogram rule, that's that one. Okay. And for each v in V, we're going to define CV to be the arrow whose length is the magnitude of C times the length of V, pointing in the same direction as V if C is greater than or equal to 0, and otherwise pointing in the opposite direction. So if you had some V here, then like this would be 2V, and this would be negative V. Okay. Others pointing in the opposite direction. And we want to show that V is a vector space that is this space, or we want to show that V is a vector space, that is, it satisfies all those conditions. And so, for example, if we wanted to show property number 2, so property number 2 or axiom 2 says that U plus V is equal to V plus U, right? And which of the pictures that we've already drawn shows axiom 2 is valid? Yeah, that second picture, because you have the U plus V is going, here's U and then V, and then the V plus U is just doing it in the other order, right? And either way, you end up in the same place. Okay. And how about axiom 4? We haven't talked about yet. So axiom 4 says that there is a 0. What does a 0 vector look like in this context? Yeah, from Croy, it would just be a dot, right? Or a point. Has no length, no direction, right? And so we could go through and we could graphically show that this world of graphical vectors satisfies all 10 of those axioms, right? So once again, this is describing a vector space. So I haven't gone through all 10, but I think you get the idea of how that would work. Here, for example, in the orange, you would get axiom 6. Right. Croy asked, so can a vector space have only one dimension? Certainly. Yeah, a vector space can have only one dimension. An example of a one-dimensional vector space would be the space of real numbers. There's lots of them, but here's an easy one. One-dimensional vector space. So if you add 2 real numbers together, do you get another real number? Yes. If you multiply a real number by a scalar, do you get another real number? Yes. Is there a 0 real number? Yes. So this is a very boring one. We're going to talk later on today, but another example of a one-dimensional vector space or subspace, maybe it's better to call it a subspace, but a one-dimensional subspace would be like the span of the vector 1, 2, 3, 4. So if you looked at the set of all of these vectors, because there's an infinite number of them, add 2 of them up, they will still be in the span. Multiply them by a constant, it will still be in the span. Is there a 0? Yep, 0 times 0, 0, 0, 0 is in the span. So this would be another example. So first and second example. Okay. Other questions here? So let's continue on. So that was vector spaces. What did I tell you about the list of 10? Did I tell you that you should memorize that list of 10 axioms? What did I say there? I said, no, do not memorize the list of axioms on the previous page. What you do want to memorize, what you do want to know is the following. So this is the one that's a big deal. So definition, a subspace of a vector space V is a subset H of V that has three properties. The zero vector of V is in H. H is closed under vector addition. That is, for each U and V in H, the sum U plus V is also in H. And H is closed under multiplication by scalars. That is, for each U in H and each scalar C, the vector CU is in H. Okay, this right here is important. And it's going to be the kind of the building block of a whole bunch of the stuff that we're going to talk about over the next few days. There was a question, I can't remember what was the question. There was a question on the last assessment that said, how would you show that something is a linear transformation? That was a question that was on the last assessment. There's probably a parallel question on the next assessment that says something like, how would you show something as a subspace? And if I asked, how do you show something's a subspace? I'm asking you to list these three conditions. Okay. You don't have to make it up. All right. And we're going to do some examples. Today is a little bit theoretical. Tomorrow we start doing examples with that, or maybe even at the end of the class today. So note, every subspace is itself a vector space. So the set of just the zero vector in a vector space V is a subspace of V, and it's called the zero subspace. Not subspace, subspace. And it's written as, it's going to blow your mind here, curly bracket or brace is zero vector and then zero. Let's make sure that it satisfies the conditions. So is the zero vector in there? Yep. It's the only thing that's there. It's closed under vector addition. So that is, if we take two things that are in this set, so my two things would have to be 0 and 0, and I add them together, I still get 0. Yay. And if I multiply 0 by a scalar, do I still get 0? Yep. So it is a subspace. It's a very boring subspace. Okay. All right, so then let's look at something a little bit more complicated here in example 3. So we're going to let P be the set of all polynomials and a subspace of the set of all real valued functions. Is Pn a subspace of P? And so we were talking about the double strike notation. And so here it looks like in my notes, I'm just using the capital P I'm just using the capital P instead of the double strike, kind of in the same place. So little p, let's see, how did you do this? This one, like in your old kindergarten class, so where you have the lowercase, this would be a specific polynomial. But if you had a big P, then this would be the space or the set. Okay. So let's give ourselves a couple of polynomials and see what happens. So let's let F1 equal to A0 plus A1 we'll use x's today. X plus a n xn, or x to the n, and f2 equal your b's, and c be a scalar. Okay, so we want to go through these three conditions. So again, the three conditions are A, the zero vector is in the space, B, that it's closed under addition, and C, it's closed under multiplication by a scalar. And so we would say, so A, we want to know, is 0 an element of Pn? Yes, no, and how do I show that? I got a yes from Abed. And what do I need to do to show that, that 0 works? How do I show that it works? We could plug it in. I'm going to go with what Ahmed said. So we could let like a naught equal a1 equal ... equal an equals 0. So if we let all those coefficients equal 0, then you're going to end up with a 0 polynomial. And so, yeah, you have a 0 in this particular set. Okay. We want to know if uv equals vu, or in other words, we're trying to figure out if f1, sorry, we're trying to figure out if f1 plus f2 is in Pn. Okay, so f1 plus f2, this would be like a naught plus b naught plus a1 plus b1 x plus ... plus an plus bn xn. Is this in Pn? Is this a polynomial? Yeah. Still a polynomial. How about scalar multiplication? We could look at c times f1. Is that in Pn? Is that an nth degree polynomial? Again, the answer is going to be yes, because you're going to have c a naught plus c a1x plus c a n x to the n. And this is again going to be in Pn. So what do we conclude from all this kind of stuff? So you conclude that Pn is a subspace. In this case, it's a subspace of the set of all real valued functions. Okay. Can you give me an example of a type of function that wouldn't form a subspace? I mean, at this point, you're like, hey, maybe everything works. So lines, some kind of lines could work, some kinds of lines might not work. So Ryan, what would be an example of a line, of a set of lines that wouldn't work? Yeah, so some linear functions will create subspaces and some linear functions won't create subspaces. And think about the conditions that might help. So all real value, oh, functions. Okay. Yeah, I think this could work. So let's look at some of the examples that you've all mentioned. I'm going to move over to the side. So if we looked at lines, not subspaces. Okay, so how about one example would be like lines not through the origin. Why? Which condition does this one fail? Yeah, the first one. Yeah, the first one doesn't work. And then I had curved. I think Richard's comment was on curved lines. Maybe you could do. Sure, let's think about these. Functions that curve. Okay. So example of functions that curve. Here's an example of a function that curves. Here's one that curves. They could certainly go through the origin. So 0 works. You could add them together. What they could go through the origin. What fails here? I've never thought of this example before, but what would fail? So suppose you had two things in it. Yeah, scalar multiplication. What's the bad scalar, Alex? What's the bad scalar? Yeah, from Ahmed, 0. So if you multiply by 0, what kind of curve are you going to get out? You're going to get out just the x-axis, right? Which no longer has a curve to it. It's kind of a funky example. So yeah, so there's a couple examples that you came up with. So nice job. Questions? Keep going. Okay, what about a, where am I at my notes? Yeah, what about a plane that is not through the origin, or a line in R2 that's not through the origin? Are they subspaces of R3 or R2? Yeah. Yeah. So one of the keys is that it'll have to be a flat surface, and it's got to include some version of the origin in its set. Otherwise, it will fail by default. So let's look at this example 4 here. So the vector space R2, oh my gosh. I feel like there's something different between my notes and what I've got here. The vector space R2 is not a subspace of R3, but H is. Okay. First of all, why wouldn't R2 be a subspace of R3? It sort of doesn't have enough dimensions. Like, these things look like XY, and these things look like XYZ. And so you can't, for example, you couldn't add 2 things in this blue side. You can't add 2 of those and magically end up with a 3rd dimension. Like, it just doesn't work. But we could just add a dummy component on the end here. We just add the 0 on the end, and now it'll work. Is 0 in the set? Yeah, in order for 0 to be in the set, you'd have S and T be 0. If you added 2 of these puppies together, it would still have the same form. If you multiply by a scalar, it would still have the same form. So this one over here is a subspace of R3. Questions?
So if a vector in R2 was ST, it would look the exact same as ST0, correct?
No, because it doesn't have enough components. Like, think about it from a programming standpoint. Like, if you were trying to add a list that had 2 components to a list that had 3 components, you would get a dimension error, basically. So, but we can fill it out. We could just add another one on to make it work.
I see.
Yeah. So it's not a subspace. We could make it a subspace, but it's not a subspace in and of itself. Good question, Abe. All right. So we're happy there. Let's look at example 5 here. So given V1 and V2 in a vector space V, let H equal the span of V1, V2. And I want to show that H is a subspace of V. So notice that I don't know how many components these vectors have. They could have 2 components, they could have 20 components, they could have 1,000 components. Okay. But if I want to show that it's a subspace, I got to show that it satisfies 3 conditions. What's the first condition I need to show? I would say Evan's right. We got to first show that 0 is in the subspace H. And remember, that subspace is the span of V1 and V2. So how do I show that 0 is in the span? Yeah, so that would work. So we did, remember what span is it's the set of all linear combinations. So you could try, so you can't list V1 twice, but we could do 0 V1 plus 0 V2. This is certainly in the span of V1 and V2. And I think it's safe to say that that's the 0 vector. So thank you for that, Evan. Second condition, as Croy mentioned, is addition. So we could add two vectors together. So let U and W that are in the space or in the span be given. Okay. Okay. So I have these two vectors U and W that are in the span. So if they're in the span, that means that U and W are both linear combinations of V1 and V2. So this means there exists A, B, C, D scalars, so in R, such that U equals AV1 plus BV2 and W equals get my letters clear. W equals CV1 plus DV2. Notice if we like to say V for vector, so what do you call a vector that starts with a U or a W? Is that like a euctor and a vector? So here you've got your euctor and your vector made up of the V1 and V2 vectors. So what we want to show is that U plus W is also in the span. So this implies that U plus W, our euctor plus our vector, is equal to AV1 plus BV2 plus CV1 plus DV2. I'm guessing everybody's seeing what's going on. So we have that this is equal to A plus C V1 plus B plus D V2. And this last thing is a linear combination of V1 and V2. So it certainly lives in the span of V1, V2. Okay, so we showed that 0 was in the set. We showed that U plus W is in the set. So we still just need to show that scalar multiplication works. So to show scalar multiplication works, we can again give ourselves some euctor U, which is in the span. take an arbitrary element that's in the set, and we're doing scalar multiplication, so we need to give ourselves a scalar C. Okay. Well, this implies that there exists A and B scalars such that U is equal to AV1, sorry, AV1 plus BV2, just like before, which tells us that CU is equal to CAV1 plus CBV2, which is, again, certainly in the span of V1, V2. Which allows us to conclude that therefore H is a subspace. Questions? All right. So what I want to point out here is that while we just had V1 and V2 in this example, we could have had 10 vectors or 50 vectors. That basically the set of vectors, the span basically generates a subspace regardless of how many vectors there are. And so this next theorem says that very thing. So it says that if V1 to V2, V1 to VP are in a vector space V, then the span of a whole bunch of vectors is a subspace of V. In our last example, we just had P was 2, so it was just V1 and V2, but now you could have a whole bunch of this. And so we call this subspace the subspace spanned the subspace spanned by V1 to VP. Well, there's a missing comma here. And for any subspace H, we call the set V1 to VP such that H equals the span of V1 to VP. We call this the spanning set. Okay. This is not supposed to be a hard concept. It is new, but this particular concept is important. Okay, and you don't need to fixate on it right now. Tomorrow, we're going to start talking about the null space and the column space. And so those are specific examples of subspaces that are spanned by a set of vectors. And we will be talking about spanning sets again tomorrow. So you don't need to get stuck here at the moment. I'm just telling you that this is a big deal moving forward. One last little example here. So let H be the set of all vectors of the form given, where A and B are arbitrary scalars. So we can show that H is a subspace of R4. And so what I want to point out is that if we have A, 3A plus B, B and A minus 2B, this is the same thing as A times 1, 3, 0, 1 plus B times 0, 1, 1 minus 2. Okay. And so another way of describing this same thing is that this is the set of vectors spanned by those two vectors, 1, 3, 0, 1, 0, 1, 1, negative 2. Or if you will, if we called these V1 and V2, we could simply say that H is equal to the span of V1, V2. And since H is equal to the span, it has that form. Therefore, H is a subspace. If you will, you could think about these. Oh, sorry, shrunk it a little bit too much. Come on. You could think about these vectors that are in the spanning set, these ones here, those ones there. You could think about these as the handles that are defining the subspace. Okay, they are they're what subspaces have an infinite number of vectors in them, except for the zero subspace. And so it's really hard to hold on to an infinite number of things at one time. And so we have these handles, or these to the VPs, that let us kind of talk about the subspace in more concrete terms. So I want to begin with an example of something that we've done in the past, but now we want to talk about it in a subspace manner. So it's basically a familiar question, just in a new context. All right, so example 7. For what values of H will Y be in the subspace of R3 spanned by V1, V2, and V3, and then V1, V2, V3 are given, and Y is given as well. And again, this is a familiar example. We actually worked through this exact question previously. So what this is saying is that if we want Y to be in the subspace here, Y to be in the subspace here, that means it must be a linear combination of V1, V2, V3. So, boy, how do we do that? I guess we've done it a whole bunch of times. So this would be like saying we need to solve for whether we need to solve like A1 V1 plus A2 V2 plus A3 V3 equal to Y. Okay, and we're asking what this would mean is the Y is a linear combination of V1, V2, V3. In other words, we added scalar multiples of the vectors, we added different combinations of the vectors, and we still stayed within the space. But this should look familiar. We could write this as matrix A, which is made up of V1, V2, V3. times our A1, A2, A3. And we want this to equal y. Or in other words, if we called this our x and this our this our a and this our x, this would be like saying we're trying to solve ax equal to y, which we've done a zillion times using row reduction. So we can set up our matrix. So we'll get 1, 5, 4. Right, so we set up our matrix. Here's our V1, our V2, our V3, and our Y. Okay. And then we can row reduce. We can add rows together. We can multiply rows by scalars. And maybe for the sake of simplicity, I'll say we've already done this in the past. And when you row reduce, you end up in a place. Come on. There. We end up in a place where we have 1, 5, -3, -4, 0, 1, -2, -1, 0, 0, 0, h minus 5. Okay. So the question is asking us, for what values of h will y be in the subspace. So first of all, what's the answer to the question? Yeah, from Croy and Ben. So we need it to be consistent, like Abed said. So we need the system consistent. So since we need the system consistent, that means we must need to have h equal to 5. If we were to do this graphically, what this is saying is, you'll notice that you only have 2 pivots. Okay, and so looking ahead, we would say that we could span this space with just 2 vectors, or our subspace only has 2 dimensions. So this is like a foreshadow. We would say that the dimension of the span of V1, V2, V3 is 2. And the reason it's 2, let me see if I can make that clear. The reason it's 2 is because there's 1, 2 pivots. Okay, so our dimension is 2, and so graphically, this span right here represents a plane in R3 through the origin. And so when we say h equals 5 is the only time this is consistent, what we're really saying is that when h equals 5, we're saying that the vector, what would it be? -4, 3, 5 is on the plane, or is parallel to the plane.
Bestie, so the vector that you have, -4, 3, and 5.
Mm-hmm.
So when h is 5, wouldn't that make the vector be 0?
When h is, when this is the vector y. So when it's this y over here. So we're saying
Oh, okay.
when h is equal to 5, that's the y vector that we'd have, and that y is in the subspace that we're talking about. So good question.
Makes sense. All right. Thank you.
Okay. Other questions? Okay. So I'd like to just talk briefly about these two practice questions. Okay. So I'm not going to work through these in their entirety, but I just want to give kind of a hint on these two practice questions. So on practice question number 1, it says show that the set H of all points in R2 of the form 3s, comma 2 plus 5s is not a vector space by showing that it is not closed under scalar multiplication. That is, find a specific vector u in H and a scalar c such that cu is not in H. And what I want to point out the fact that 0 is not in the space either because of this 2 that's here. That kind of 2 is kind of weird. But you could imagine taking, you could imagine that if s was equal to 1, that tells you that then you'd have 3 comma 7 is in the space. So then suppose we chose a scalar. Maybe we could choose a scalar like, I don't know, 2. Let's not overthink. And so what we're asking is 2 times 3 comma 7 equal to 6 comma 14 in the space. And it should be pretty obvious that it's not, because in order for this to be true, s would have to be, here, s would have to be 2 in order to make the 6 work. But if you made s equal to 2, the 14 wouldn't match. And then same thing, Ahmed, if we chose 0, we would get a 0, but 0 is never going to be of this form right here. Does that make sense, Ahmed? Yeah. So there's kind of most of practice question number 1, just a little bit of a hint there. And then in question number 3, there is no question 2, by the way. It says an n by n matrix A is said to be symmetric. That is, the transpose equals the original matrix. That's what it means to be symmetric. So if we let S be the set of all 3 by 3 symmetric matrices, we want to show that S is a subspace of M3 by 3. This M3 by 3, this would be the set of all 3 by 3 matrices. Okay, which is, I guess, what it says then next. So if we want to show that it's a subspace, what are the 3 conditions that we need to prove? We got to show that there's a 0 vector. We got to show that it's closed under addition, and we got to show that it's closed under scalar multiplication. Thank you, Felix, Ryan, and Anthony. That's exactly right. So maybe think about what these symmetric matrices look like. These guys are going to look like, you could have like an A, B, C. But if you have A in the 1, 2 spot, then you must have B here as well. D, E, C, E, F. So these would be symmetric matrices. And again, notice that you have B here and B there, C here and C here, E here and E there. So that's what symmetric matrices look like. And so basically you're going to have to show that matrices of this form that matrices like this include 0, so that's the first condition. Secondly, are closed under addition. And third, hey, sorry, I unshared. Come on. Closed under scalar multiplication. Okay, so you want to choose the general case, so kind of the punchline. And when I say general case, what I'm saying is don't choose numbers. You want to keep letters in there. You want there to be A, B, C's, D's, things like that in your arbitrary vectors.